All right, this is Pre-Calc Appendix A.1. Some skills for today. We are going to look at simplifying and evaluating radicals and rational exponents. We're going to look at reducing, factoring, and simplifying rational expressions. And we're going to review how to rationalize the denominator and exponents. This section is to help you practice manipulating expressions using skills and properties that you've learned in the past. You may be rusty. Your skills will improve by implementing a simple three-step procedure. Step 1, practice. Step 2, practice. Step 3, practice. These techniques require a lot of practice to be able to do them well. All right, so we're going to look at radicals and rational exponents and review the properties of those. Our first definition is about an nth root. It says let n be an integer greater than 1 and a and b be real numbers. If b to the nth power is equal to a, then b is called the nth root of a. If a has an nth root, the principal nth root of a will be the nth root having the same sign as a. The principal nth root of a is denoted by the radical expression written here. The positive integer n is called the index of the radical, and the number under that radical symbol is called the radicand. Now, a couple things to keep in mind. When you first learned about square roots, you learned that you couldn't square root a negative. Then you learned how to deal with that with imaginary numbers. But in this course, we're strictly looking at real numbers. So, first thing, if n is an odd number, if that index is odd, then you have exactly one real root. The issue is when it is even. When n is even, positive real numbers will have two real roots. Negative real numbers will have no real nth roots. So we're looking at this radical symbol. Okay. If there is no index listed, then we're talking about the square root. We typically don't write the little 2 in there for a square root just because it gets a little messier and it's not needed. If a is a positive real number and n is a positive even number, then we said that there are two real nth roots, and we will write them like this, one with the positive, one with the negative. And sometimes they put that together like that. All right, let's try a couple. First one, square root of 36. There is no negative in front, there's no plus minus in front, they are simply looking for the principal root, and since 36 is positive, we are looking for a positive 6. Our next one, we are taking the cube root of a fraction. You can do that by taking the cube root of each piece, and the cube root of 27 is 3, and the cube root of 8 is 2. Question C is almost identical, except there's a negative sign in there. And we said if this is odd, it's fine. You can take the root of a negative. So we are just simply going to get the same answer we had in part B, except it's negative. Question D, we're taking the fourth root of negative 625. Since this is even and this is negative, there is no solution to that. E is asking for the fifth root of 32. That would be 2, since 2 to the fifth is equal to 32. 2 would be the root. The fourth root of 625 is 5. The cube root of negative 27, we did that one up here as well, would be negative 3. And the sixth root of 64 is 2, because 2 to the sixth gives us 64. Now, you do have a root key on your calculator, so you can check some of these. However, we want you to do as much as possible without the calculators. All right, some properties of these radicals. It says let u and v be real numbers, variables or algebraic expressions, and m and n are positive integers greater than 1. We'll come back to this statement. It says we assume that all of the roots are real numbers, so we're not dealing with imaginary, and all the denominators are not 0. Okay, first property. it says if we are taking the nth root of a product, u times v, we can split that up and take the nth root of each factor individually first. Our example here, we have the square root of 75. Since 75 is not a perfect square, we typically look for factors that are. So we would split the 75 into 25 times 3, and then the square root of 25 is 5. So we end up with simplified answer of 5 root 3. The same idea happens in example 2, only difference is we are dividing instead of multiplying. We have an example, the fourth root of 96 divided by the fourth root of 6. Neither of those are perfect fourths, but if we put them together, we can divide the 96 by 6 first. We end up with 16, which does have a perfect fourth root of 2. Question 3 says if we are taking a root of a root, you can multiply those two indices and then take that final root all as one. So our example here, we are taking the square root of the cube root of 7. So multiplying the 2 times 3, that is the equivalent to saying the sixth root of 7. We're going to come back to number 4 in just a sec. Number 5 says take the nth root of u to the nth power. And they are saying that is equivalent to taking the nth root of u first and then raising it to the power. In other words, it doesn't matter if you deal with the index first, the root, or if you deal with the power first. Both will get you to the same answer. So in this example, we have the cube root of 27 squared. Well, I don't know what 27 squared is off the top of my head, but I do know that the cube root of 27 is 3. So if I do the cube root first, I can get that down to a 3, and then I know that 3 squared is 9. All right, take a look at properties 4 and 5. They look very similar. The difference here is that in example 4, we are taking the nth root of u first. And based on our earlier statement that if we are taking an even root, u would have to be a positive number. And we are assuming, like I said up here, that all of our answers are real, that they do work. So in this example 4, they are assuming that u is positive when n is an even number. So we don't have to worry about the other options happening. All right? And basically they're saying if we take the nth root of something and then raise it to the nth power, we've basically canceled each other out. So our example, the fourth root of 5 to the fourth power is just a 5.